Well, good afternoon online and here in person in Kuiper. I'm delighted to have the opportunity to introduce my friend and colleague, Dr. Heidi Hammel. She is both the JWST Interdisciplinary Science for the Solar System and the RF Vice President for Science. She oversees science from all aspects of RI, including the Space Telescope Science Institute. Heidi is a scientific granddaughter of Gerard Kuiper. She was pointed out to me today. One of Kuiper's last students was Dale Cruikshank, and Heidi received her PhD under Dale at the University of Hawaii in 1988. For her thesis, one thing Heidi worked on was observing Neptune ahead of the Voyager encounter to understand what Voyager would be seeing. And in fact, as a graduate student, I remember seeing a talk Heidi gave on this at the Paris DPS, which I had to look up back in 1986. Working on these topics for a long time. When I was in New Mexico State, Rita Beebe used to tell the graduate students, "Be nice to your cohort because you keep seeing them through your career." And I think Heidi and I have run into each other a lot in the course of the last 30 years. Heidi's going to be telling us about her work on the first year of JWST.
Thank you very much. Can you all hear me in the back of the room? Is the microphone working? Super. So it's great to be here. Great to see old friends. Great to meet new faces. I would like to share with you today a bit of a public lecture. This is not going to be a hardcore science seminar. That will come. But right now, we're still in the glow phase of the fact that JWST is up and working. And so what I'm going to do today is really start with the basics. We're going to talk about light. We're going to talk about spectroscopy. Then I'm going to be showing you some of the newest JWST images, many of which you will have seen, but I'll talk a little bit about the science in those images. I'll share with you a bit about my program of guaranteed time, which is all solar system. And then I'll talk about the future, what comes beyond. So let's start with Newton and talk about light. What Newton did, of course, is he put a prism in a pinhole and showed that white light from the sun is actually a rainbow of colors. But we know, those of us who work in this field, that rainbow of colors is only a tiny piece of the electromagnetic spectrum. And in fact, there is light spanning both shorter and longer wavelengths. And you know these names for these different kinds of light, all the way from the high energy gamma rays, X-rays, UV visible, to the longer wavelengths, longer than red, that we can't see with our eyes, like the near infrared, mid-infrared, and moving on into the microwave and the radio. And astronomers care about all of the colors because the universe emits light in all of the colors, not just the visible. And so we want telescopes that cover all of those wavelengths. And in fact, we've built telescopes that cover all of those wavelengths. And today we'll be talking mostly about infrared, talking about why JWST is designed to be in the infrared. Infrared light reveals the invisible. Here's a standard picture of a guy holding a trash bag up at visible wavelengths. But if you then look at him with an infrared camera, you can see through the bag and you can see inside the bag. And that's true in astrophysics too. So we can see things that are hidden. In astrophysics, it's not garbage bags, it's dust. Dust hides things. JWST, with its infrared capability, will see through the dust. I also want to stress that infrared light is also heat, right? It's the same thing. And so we are seeing the heat from the universe. And so in the cosmos, here's an example of an object that many of the people who are amateur astronomers, I'm sure you recognize this object. No? Orion, thank you. And you're aware that here in his sword, there's a little nebula called the Orion Nebula. This is a visible wavelength image. And so if we look at this same object, this same asterism with an infrared camera, this is what you see. So the heat of the dust is revealed to you. And you see that what we're seeing here in visible light is just a little tiny opening in a vast dust cloud that is allowing newborn starlight to peek out, but it's all invisible because of the dust that is blocking it. So with the infrared cameras of JWST, we'll be able to probe through all of that. So now let's turn to spectroscopy. Spectroscopy is the superpower of JWST. So every JWST public lecture explains spectroscopy. When we look at that rainbow of light that we showed you what Isaac Newton found with his prism, if there are certain kinds of molecules or atoms in between you and the light, they can absorb colors. And that spectral fingerprint, that black lines of missing light, tell you what the composition is of the molecules, gases, dust, whatever it is in between. In some cases, under certain conditions, though, you can actually have light added to the spectrum. That just has to do with the pressure and the temperature, and I'm not going to go into the details here, but just trust me, it happens. So there are times when light is added. But back in the day, when Mark and I were young students, we did not have color printers, so we couldn't print things like this, right? So how were we going to display it? We came up with a technique of drawing a line, and where the light is missing, you have a dip. And where the light is added, you have a bump. And this squiggly line is a spectrum. Now, in the early days, NASA prohibited us from talking about squiggly line charts. It was a no-no. Those of us who are old enough remember those days, and we are like, we're beyond that now. JWST is creating spectra. Hubble creates spectra. That is the tool that we use. Here's an example from Hubble. A beautiful exploding star, Eta Carina. It's a massive star, and it is exploding and injecting lobes out from the explosion site. But that picture doesn't tell you the whole story. What you really want to do is put a slit there and spread out that light into the spectrum, because then you see lines that tell you the composition of the materials there. And it's argon, it's nickel, it's iron. You can actually sense the atoms and the molecules in that dusty nebula. And if you look carefully, some of those lines are kind of cockeyed. That is due to motions in this material. So the true science from these telescopes comes from the spectrum. That is what tells you composition, temperature, pressure, dynamics. There's kind of a joke that's being circulated now. If a picture is worth 1,000 words, a spectrum is worth 1,000 pictures. So we're going to be showing lots of spectroscopy from JWST. So you needed to understand that whole background on why. And let's talk about some other science. This is the astrophysics part of spectroscopy. A nearby star has typically a spectral fingerprint due to hydrogen that looks something like that. And those lines, alpha, beta, gamma, delta, are certain lines due to the sort of the quantum physics of hydrogen, if you will. But if you look at a further star or a nearby galaxy, if you look closely, you see those lines are all shifted just a little tiny bit. But if you look even further, a very distant galaxy, now there's a noticeable shift to the red. And if we look at some of the very most distant galaxies that we've been ever able to see, really distant galaxies, that redshift is huge. And that redshift is caused by the expansion of our universe. Not only is the universe itself expanding, but the light that is traveling from those distant objects is also, the wavelengths of the light are expanding, and that shifts them to the red. So if we want to see the hydrogen in the most distant galaxies, we cannot look in the visible. We must look in the infrared. And that, my friends, is the raison d'etre for James Webb Space Telescope. It is designed to see the earliest galaxies that have ever formed in the universe, maybe even the very first stars, which are probably hydrogen, completely hydrogen. So to see those hydrogen lines, we must look in the infrared. And that has driven everything about this telescope. That is why it is an infrared telescope. So here's one of our cosmological cartoons showing you from the Big Bang all the way out to the modern day. We're at the other end of that horn shape. We want to see the first stars and the first galaxies from the first stars. So kind of turning this sideways and comparing it to that chart, that shows you why we must look in the infrared. So everything about this telescope is designed for infrared. And that is why it looks so strange and different from many other telescopes. That's Hubble to scale with JWST. So one obvious difference is its mirror is silver, this mirror is gold. And gold was chosen because it is an extremely effective reflector of infrared light. That is exactly why gold was chosen. Also, Hubble and most of our other classic telescopes are enclosed in tubes. JWST is not enclosed in a tube. Any guesses as to why that is? Relates to something I said earlier about what is infrared light.
Tube will heat up.
The tube will heat up, and that heat from the tube will swamp the infrared flux from the very distant galaxies. So everything about this telescope is designed to keep it super cold. And this giant sun shield, which is the size of a regulation tennis court, is also designed to block light and warmth from the sun and the earth and the moon, so that we keep the telescope and the instruments extremely cold. They're on the cold side of it. So we're not putting this telescope in low Earth orbit like Hubble. And why is that? Because Earth is hot, it's warm, and the moon is warm. So we want to put this telescope as far away as we can. Just wanted, for those of you who are really into the details, I wanted to flash up a chart that shows you in wavelength on the bottom axis from the visible, starting at 0.6 microns, all the way out to the thermal infrared, 28 microns, the different modes that we are going to be observing in the infrared. Imaging at the top, spectroscopy at the bottom. So the spectroscopy is a huge part of what we're going to do, but lots of images too. All right, so I already mentioned the first light. That's a key science theme. As I said, that was the reason we built this telescope, but we have other science as well. We're going to be looking at the assembly of galaxies over time, because if you can see the first galaxies, that means you can see all the galaxies in between as well. And so how they evolve over time, key science goal. We'll also be looking at the birth of stars and protoplanetary systems, because we'll be able to see through the dust clouds where these things are being formed. And then what brought me here to you today is a theme about planetary systems and the origins of life. That's another key science theme that we'll be talking about. Okay, so this all was like Merry Christmas. We're just now into the Christmas season. We're after Thanksgiving. Christmas Day was when we had the successful launch of JWST on an Ariane 5 rocket from the spaceport at French Guiana. It was in French Guiana because it was an Ariane 5. That's what we launched on. It was a contribution from the European Space Agency. This is a joint NASA, ESA, and Canadian Space Agency project. So let's watch that and a little bit of narration perhaps. In French, because it's French Guiana. I was so nervous, I couldn't sit down. I was pacing when this was all happening.
James Webb begins a voyage back to the birth of the universe.
See that woman hyperventilating? Yeah, that was all of us. All of us. We were like, nominal was the word of the day. This was a perfect launch. It put us on a perfect trajectory to L2. And it was so perfect, in fact, that they had a little camera inside the rocket fairing. And so what you're seeing here is the last view of the telescope as it separates from the rocket fairing. And you can see little retro rockets firing, you see little blue glows picking up around there. This was supposed to take about 3 minutes before it deployed the solar panel. And it went off early because the launch was so perfect. It put us exactly on the right trajectory. And so we were all scared when the solar panel deployed because we're like, oh, that's too early. But it was actually because it was so good. So, oops, I hit the wrong button. Start again. Right, we do that, and we do that. There we go. So JWST was so large, the mirror and the sun shield, tennis court size sun shield, that it had to be folded up to fit inside the fairing of the Ariane 5 rocket and then deployed as it is en route to the L2 point. And we're putting it at L2 because we want to make sure, go back here, because we want it to be far away from the Earth, and L2 is a gravitationally stable point. It took a month to travel to L2, and during that month is when all the deployments took place. The telescope unfolded, sort of a reverse origami, if you will. And there were something on the order of 400 different deployments that had to happen, of which about 100 were single point failures. If they didn't happen, we didn't have a telescope. So this month was a very long month, but everything worked perfectly. And the further we got, the more nervous we got, because you just don't expect everything to be perfect, but it was. And so after a month, we were there at L2. And L2 is a point that is a straight line from the sun to the Earth, and then another 1.5 million kilometers. So there's no servicing happening. It's 4 times the distance of the moon. And only last week has NASA gone back to the moon with an uncrewed rocket. And so we're not going 4 times further than the moon to service this. It had to be perfect, and it was. And I like to show this one because we see a lot of pictures of JWST that look like this, but in fact, remember what the purpose of the sun shield was? It looks like this all the time. And so the direction that we can point is always sort of in a circle. We can't tilt the telescope to point exactly away from the Earth. So we can never look at opposition. Planetary astronomers, I'm sorry, no opposition surges for you. But we can see in a torus around that. And of course, this is moving around with the Earth's orbit around the sun. Okay, so we were at L2, took us a month to get there. Then it was 6 months of focusing the telescope, because remember, it's 18 segments, and then another 6 months of calibrating and commissioning the instrumentation. So we really did not start our science program until July. I thought I'd show some pictures. Maybe you haven't seen these. This was the first star image that we took with JWST. And that's one star. But because all the mirrors, when it was launched, were all a little bit askew, you get 18 weird, different little images of the one star. So the first thing that was done is we would move one mirror at a time and see which one of these things moved. And then we would move it to a location that kind of represented the shape of JWST, just to keep track of things. And so after we identified all of those, we had a picture that looked like that. That's still only one star. And you can see a lot of them are really out of focus and nasty. So the next step would be to focus all the individual mirrors and then bring them together into a single image. And then what you would see after that was this. And what blew us all away is even in this calibration image of a single star, the background is filled with little splotches, and each one of those is a galaxy. So even our calibration image from JWST provided a deep field of distant galaxies. And this was like 75-second exposures, super short. And this just like, we're all starting to lose our minds because it was working and working fabulously. So now here is, once we spoke, this was all done with the near cam, the primary camera that will do the tracking and guiding. Then we had to do the field focus so that all the other instruments were in focus as well. And so that's why it took 6 months of work to get this all working. But it did. So I wanted to show you why we're all so gaga. Here's an image from the WISE infrared telescope at 4.6 microns. Here's an image from Spitzer at 8 microns, so another infrared wavelength, and you see the increase in resolution. Now I will show you the JWST same field. And so you can see the astonishing change in the spatial resolution and the sensitivity of that field as we move from a smaller telescope to our larger, incredibly sensitive telescope. And this is why we're going to be rewriting history books, because we're opening a whole new realm of infrared science. So now let's talk about the images that you may have seen. The first deep field was actually not chosen to be a super deep field. It was chosen to be a really cool looking deep field. This is a cluster of galaxies. All these, let's see if I can do this. All of these fuzzy white blobs here in the center are all galaxies that are all part of a cluster. They're all together in space. And each galaxy, I'm now speaking to my planetary science colleagues, making sure you know, each galaxy is made of billions of stars and, tens of billions of planets. So when you put all those galaxies together in a cluster, the gravitational mass is so huge that it distorts space-time. It bends space, and space itself acts like a lens for things that are even further away. Einstein predicted this, and of course, Einstein, being Einstein, was right. Every one of these streaks that you see that, if you look carefully, sort of form a circular pattern around here, those are distant galaxies that have been refocused by this distortion of space-time by the local galaxy cluster. And they are more distant galaxies that we can probe with JWST. I should mention too that there are some photobombs. Anything that has this beautiful point spread function, this star stuff that looks like that, those are all foreground stars that just are photobombing the image. But everything else that you see here that does not have this diffraction spike, everything else is a galaxy. And some of these galaxies have been found to be among the most distant galaxies ever detected. Just in this first image, which was a 12.5-hour exposure. And I mention this because some of you who follow this kind of thing may be familiar with the Hubble Deep Field. That first Hubble Deep Field was 10 days of exposure. And this is 12.5 hours. And this isn't even one of our deep fields yet. And we're already picking up some galaxies that are more distant than we've ever seen before with Hubble. So let's do a little zoom around here just for fun. I like to just look close in. Is a nice close-up of the galaxy cluster itself. Now we move off to the side away from the cluster so that you can see some of these incredibly faint distant galaxies. And the whole field, everywhere you look, is packed with galaxies and weird distortions of more distant galaxies. So some of them are red, those are probably further ones. Some of them are closer. You can see their spiral structure here and there. So just give you a sense of how rich just this one single image is. Okay, so let's talk about some of the spectroscopy that we do here. We pick out some of the faintest objects here. Oh, that's a Hubble image, by the way, of the same field, just to give you a sense of how much deeper we're probing with JWST here. So here is some spectroscopy of some selected galaxies in that field. You remember the cartoon I showed you with the hydrogen lines marching outward? Well, here's the data. You can see hydrogen and oxygen lines, and the further you go in time, the more distant you go, you see them march right out to the infrared. So this is real data showing exactly what I had described to you, which is, of course, the way science works. We have theories, sometimes they're confirmed. So you'll be hearing a lot about very high redshift galaxies. Some of the most distant ones, the ones that we think are the highest redshift galaxies, to the astrophysicists here, I'm talking of Z of 11. Some people have even claimed Z of 22. Those are photo Zs. They aren't spectroscopy yet. I'm just speaking to the astrophysicists. So we have to wait until we get the actual spectroscopy to confirm some of the very highest redshifts that have been reported. But again, this is just a preliminary image. It's not our deep field. There's no question that we will be able to shatter the records and see some of the first galaxies that have ever formed. And what we're finding scientifically is in these very distant galaxies, they're actually brighter than people had anticipated. And so the question that is still being debated and will not be resolved for a while yet is there something that we don't know about early galaxy formation that is causing these earliest galaxies to be brighter than normal? Or are we just wrong about their redshifts? And maybe they're a little bit younger than we thought. That's not resolved yet, but stay tuned. It'll be resolved in the coming months, weeks, years. So here's just an example of what a super distant galaxy may look like. One of the big programs, the GLASS program, was trying to find them. And here's a candidate. There are now, I have showed 2 papers here, but I think we're over 24 papers now reporting very high redshift galaxies. So JWST is totally delivering on the science it was designed to do. Let's just show you one more spectrum of a very distant galaxy. What I think is cool about this is that we are looking at some of the most distant objects in the universe, but we are measuring the molecules in those galaxies. Even at the edge of space-time, we can measure the molecular content of those galaxies. That's just kind of a bit of a mind-blowing thing. All right, so let's push the right button and move onward. Let's talk about the birth of stars. This was another super beautiful picture. I like to zoom around here to show you some of the detail in here. What you're seeing here is actually a huge dust cloud. And way up above, sort of out of the field of view, are some brand new stars that have been born. And they're blowing out really fast, high energy winds. And those winds are blowing into the natal cloud from which they formed and pushing it away, leaving this big empty space. And as it pushes into it, there are clumps that stick out, like the big clump up there, but there's lots of other clumps that stick out. And those clumps are where stars are being born. So they're higher density. And that's when this wind is blowing against them, it leaves this column standing. This inset is now a longer infrared image from JWST, where you can see, as we talked about with Orion, how the dust disappears, leaving you sort of the underlying skeleton, the deep part of where stars are being born. And stars are poking out up at the top that were hidden before. Like this one is really bursting out of that higher density area. Here's another cluster of new stars, and you can see some ones that are really glowing, but they haven't quite gotten out of their new environment yet. So this telescope is going to really do some fabulous work looking at how the mechanics of how stars and around those stars, how planetary systems will be forming. Here's another beautiful example of the Tarantula Nebula, where you can see, again, a cluster of brand new stars, the hot blue stars in there that are blowing away, forming a cavity of dust around them. So one of my fellow IDSs, fellow interdisciplinary scientists, is Mark McCaughrean, and he is focusing specifically on this topic for part of the science that he is doing. Let's talk about the later stages of a star's life, the end stages of a star's life. This is a Hubble image of a circular nebula called the Southern Ring Nebula, taken with Hubble. And here's another example of the power of a 6.5 meter telescope. When we look at the same nebula with JWST, the remarkable amount of detail and structure that was just simply hidden to Hubble's 2 meter aperture. And it's a beautiful example of a star that is ejecting shells of material as it reaches the end stage of its life. But there's a little trick in this picture. And you might not notice it unless you really zoom in and look carefully. If you look super carefully at what looks like the central star, you'll notice actually that there's something here going on. There's a little blip. See a little blip right there? And when we use the infrared cameras on JWST to image this same nebula, something astonishing popped out. And that is that star, that little star there, is actually the star that's creating the nebula. This star is photobombing. He's just in front, and he just happened to be near the center. So it looked like it was the star that was creating the nebula, but it wasn't. This star is still encapsulated in a thick dust shell, which is why it was invisible at the shorter wavelengths, but at the longer wavelengths, the dust is radiating heat. And that's why we see it here. So that was a fun little surprise in this nebula. Studying the details of this and many other planetary nebulae, we call them planetary nebulae just because they're kind of round like planets. They have nothing to do with planets. They are the late stages of stellar ejection. That will give us a lot of insight into the mechanisms by which stars end their life cycles. So there'll be a lot more work on such things. Okay, let's talk about galaxies too. This was one of the early release images of an object called Stephan's Quintet. There are 5 galaxies here. There's 2 here, right? And they're interacting. So 1, 2, 3, 4, 5. But one of those galaxies is not like the others. You notice this one, look how you can actually see the individual stars in this galaxy and the clumps. They're very evident here. But when you go to the other galaxies, they're not evident. They're smooth. That's because this is a foreground galaxy photobombing the cluster. It has nothing to do with this collection of galaxies, which are in fact interacting. All that red material you see is dust streamers that are being pulled out of the various galaxies as their gravitational forces interact with one another. And this guy's just along for the ride. He has nothing to do with them. So we've actually done some spectroscopy of the topmost galaxy because we believe that it harbors a black hole up there. And so when you move to the infrared, the far infrared, again, what you see is star formation all over the place, but particularly up in that top galaxy, some really bright stuff going on. So when we focus on that and do the spectroscopy, when you do spectroscopy off of the core, you see sort of standard star stuff, right? Argon, neon, sulfur, oxygen. But when you do a spectroscopy on the core, where the black hole is thought to be hidden, one of the things that really pops right up there is this broad silicate emission absorption band, which we believe could be evidence of the accretion disk of dust around the black hole. And so by using the spectroscopy, we're able to really pull out the physics and chemistry of what's happening in the core of that galaxy. Just another example of why spectra really matter to us. Here's another beautiful image. This paper just appeared the day before yesterday, so it's very new, and it's cycling between the blue Hubble image and the pink image from JWST in the infrared. And so you see what happens is spiral arms that are dark to Hubble are popping out because they are regions of star formation. So hot stars are embedded in the dust. You can't see them in visible wavelengths of Hubble, but the infrared capability of JWST allows them to pop right out. So understanding the dynamics of star formation in galaxies is going to be the role of the FANGS project that Janice Lee, who is over at Noir Lab next door, leading. She's leading this project. So tons of great galaxy science coming. And now, what you all came here for, maybe, our solar system. Just about everything I'm going to show you, not all of it, but just about everything is from my program of Guaranteed Time with JWST. And what can we observe in the solar system? Remember where JWST is located. None of the pictures are to scale here. We're located between the Earth and Mars, and we are always looking away, right, in that torus that I showed you. And so what we can observe is basically near-Earth objects outward. And the near-Earth objects have to have their orbits popping outside of this circle. And there are some that we can observe. Everything else in the solar system is fair game for JWST. And so the program we designed was to cover a sampling of brightest, fastest, faintest, sort of all the superlatives we could imagine in the solar system to demonstrate the capabilities of JWST. So let's talk about it. By the way, I was the PI, but I gave away all of my time. I did not retain a single minute. It was all given away to all of these different members of the community. Each one of them has a team of sometimes 16 or 20 people, international team. And so these people are the ones who are actually doing the science. I am but the cheerleader at this point. So I just want to make sure I acknowledge all of my fabulous team members and make sure they get full credit. Okay, so this was a test that was done during commissioning to prove that we could actually track a moving target. And that little ball that's more or less standing still is a little asteroid called 6481 Tenzing. And this was just a test to prove we could do moving target tracking. That was never guaranteed. In the early years of the project, moving targets had been what we call a level 1 requirement. But about 3 years into the project, we got an email one day and they had new level 1s. And I opened it up and I'm looking, and moving target tracking was gone. It's no longer a level 1. And that's like a death knell for a capability. If you're not a level 1, when the funding gets tight or the schedule gets long, it doesn't happen. And you all know the story of JWST with the funding and the schedule. So it was actually like about 7 years of work on my part and Jonathan Lee's part, supported by the Science Working Group, to get this moving target tracking capability restored. And thank goodness they did. Because otherwise I wouldn't be able to show you this. This is one of the pictures from Imke de Potter's early release science program of the planet Jupiter with JWST. This is a composite of several different filters. And even in this very first early image, there was surprising science. Some of the things were not surprising, things we expected to see, had hoped to see, planned to see. Things like the auroral belt, the aurorae. You see these little red lines here? In Hubble images, the aurorae are imaged at ultraviolet wavelengths, but there's no ultraviolet on JWST. What you're seeing here is H3 plus emission that we can detect in the infrared. So we can directly image the aurorae, the auroral ovals on Jupiter in the infrared. It's subtle, but I think you can see it right through here. And then there was this red glow, which is auroral activity extending up to higher altitudes, which surprised a lot of people. We were like, I didn't expect to see that, but there it is. Okay, well, let's work on that. And it wasn't just the northern hemisphere, swirling down to the southern hemisphere, same thing. I think it might be even easier for you to see the auroral oval here. You can see that striation on the planet. And I believe that this little blob here, I think that's the footprint, the auroral footprint of Io, the moon Io, which manifests itself in the aurorae. And again, that extension of the auroral activity. So hopping backwards, one of the most surprising things of this image was this strange line here along the edge. This is the shadowed edge of Jupiter, right? This should be dark. There should be shadow here. And yet there's this emission line of something. And I remember the first response from some of my non-specialist colleagues, well, your telescope's not in focus, obviously. We're like, no, totally in focus. Yeah, telescope's in focus. So that's not a ghosting effect. It's something real. And it set off a huge debate in the atmospheric community. Like, what is that? And all the usual suspects were involved. Eric, I don't know if you were involved, but everybody else was like all into it. And 3 weeks ago, I was in London, and then I was up at Oxford and Leicester, England. And the team in Leicester, they think they've cracked this. What they think this is a high altitude day glow. This is a fluorescence from H3+, but instead of being located at the poles, it is actually being distributed all around the planet. And we're seeing it here at the edge because of the high optical depth that we're going through there. So this is still not published. This is still all of us talking about it, but it was a very unexpected result. And we had never seen this with spacecraft who have visited. And so it's very interesting that in some of our very first images of Jupiter, we're coming up with new science we had not anticipated. There's, of course, the Great Red Spot. It's not red because this is not visible wavelengths. This is infrared wavelengths. And at these wavelengths, there's a lot of absorption by methane in the atmosphere. And so to get a bright thing, you have to be located above the methane absorbing layers. And so this tells us that there's a high altitude cloud component centered on the Great Red Spot. And in fact, if we zoom out again, the whole equatorial band is filled with high altitude clouds. And there's lots of convective cells, thunder clouds that poke up high in the atmosphere. Something to keep an eye out is we have done some very detailed imaging of the Great Red Spot at many, many wavelengths. And so my colleague Lee Fletcher at University of Leicester is going to be building, we hope, a three-dimensional sort of a model, but based on real data from JWST of the whole structure of the Great Red Spot from the highest altitudes down to the deepest that we can sense. So we'll have like a really great three-dimensional measurements of the Great Red Spot. So that's in the works. Okay, so zooming out, I wanted to show you a single, just a few images that are focusing on the rest of the system, where you can see that the rings pop right out. Did you know Jupiter had rings? This is a planetary group, so I hope you knew that. But I think what's important about the rings, and I want to emphasize, is that these rings are 1 million times fainter than the planet Jupiter. And yet we could just directly image them with JWST. That tells you how exquisite our point spread function is and how great this will be. All right, so I like this picture because it shows you one of the classic Hubble deep fields. But if you zoom out on this picture, something else pops into view. And that something else is one of my favorite planets. It's the planet Neptune. Remember we were talking about rings popping out? The ring system here just jumped right out of the JWST image. That blue star, that's no star. That is Neptune's moon Triton. And it is so bright that it reflects so much light that it just dominates at these infrared wavelengths. Let's zoom in a little bit on Neptune because, You know, this is one reason I joined this project 25 years ago, was to get images of Neptune. And I have to tell you just a little anecdote. When this popped up on my screen in my basement office, I started crying. I'm like, oh, it's so... And then I started jumping up and down, and I called my mom, and I called my kids, and I took my cat, and I held my cat up, and look at Neptune, look at the rings. Those rings, we haven't seen those faint rings since 1989. Voyager was the last spacecraft to be able to detect them. We tried with Keck and Hubble, and they're just too faint. So there they are. So another promise fulfilled. So happy. Now this is a teaser. These were 4 exposures taken by the education and public outreach team to make this pretty picture. We haven't gotten our Neptune science yet. This window closed before our science program could execute. The next Neptune window opens in the spring. So stay tuned for science. We weren't allowed to science these images. We weren't allowed to. So there you have it. I'm actually working on a blog that actually talks in more detail about the individual exposures. I'm running out of time, so I'm going to speed up a little bit. I just want to give you a flavor of what we see. We did image Mars. Here's a cartoon showing you our fields. The near-cam images of the surface showing you albedo features. The thermal map of Mars over there showing you the Hellas Basin. It's not cold, although it looks darker. It's actually darker because there's higher pressure at the bottom of the basin. And so there's broadening of a carbon dioxide line, and that broadening spreads out the light so that it looks colder. So it's a pressure temperature combination there on Mars. And there's also lots of fabulous spectroscopy that Geronimo Villanueva is leading. This is just a taster. The problem with Mars is it saturates. It's so bright. So he did a really good job pulling out pieces of unsaturated data that show you some of the spectroscopy and some of the chemistry we're going to do on Mars. And yes, we will be looking at methane on Mars to see what we can see of the ongoing controversy of whether methane is there and where and why and how and does it vary. So that's all still to come. We did observe the DART impact. This is a picture from Los Cumbres, where you can see the ejecta debris, but those fields of view are Hubble and Webb. And so you can see the beautiful images that we are able to get. And in fact, JWST was able to get a movie. Let's see the movie. Yeah, there it goes. If you look closely, you can see little clumps flying off there. And remember, we're looking right at the core here. And so there's some very interesting science that Christina Thomas and Andy Rivkin are going to be pulling out of that information. The moving target tracking required for DART was more than 3 times over the limit. So we actually did break a few things, but that's okay. We know what we broke and we were able to fix it, but they told us we're never allowed to go that fast again. So we did. I'm showing you some pre-planning now. We do have a program to look at Europa and Enceladus to look for plumes of material ejecting from their poles. It's coming soon, like really soon. So in a week or 2 or 3, keep your eyes out for that. We do have a program on Titan to do spectroscopy, spatially resolved spectroscopy of Titan. That's coming soon as well, like maybe in 2 days. And then ice giants, my favorite topic. I already mentioned the Neptune window is coming in the spring. The Uranus window comes on December 23rd. That's when we might get the first Uranus data. So I'm really looking forward to that. Okay, so I want to finish up here just by mentioning there's more to come. Asteroids, comet, lots of Kuiper Belt objects, Chiriclo, an occultation. So stay tuned for more solar system stuff. But wait, there's more. There's a whole lot about planets around other stars. Transit spectroscopy is the tool we use to study their atmospheres. We watch the host starlight going through the atmosphere, and we do it at multiple wavelengths. Oops, go back. You can see different colors here have different depths And that allows us to use that information like spectroscopy, if you will. So here's an example of WASP-39b, many different transits as a function of wavelength. I'm going to skip forward here to show you an example of carbon dioxide observed on WASP-39b. And there's lots of other great spectroscopy. I don't have time to do it all today, but I wanted to use this as an object lesson because there are other planets that we're going to be looking at. The TRAPPIST-1 system is a really popular one because it's got 7 kind of Earth-sized planets, 3 of which might be in the habitable zone. And my question is, can we really differentiate between the exoplanet conditions based on this spectroscopy? And my example is 3 other spectra at infrared wavelengths. And these 3 spectra show carbon dioxide, just like I showed you, as well as some other things, water, ozone. And these are Venus and Mars and Earth. And at low resolution, these spectra, they all kind of look alike. They all kind of look like WASP-39b, right? So my question is, when we go to TRAPPIST, and can we really differentiate? Is this a sign of a habitable world, or is it a Venusian hellhole, or is it a Martian, terrestrial? You can't breathe the air there; it's too thin. Or is it a nice temperate planet like Earth? It's going to be tricky with JWST. It wasn't designed to do this. And so if we're super lucky, we may be able to have enough spectral resolution to pull out some of the other stuff and maybe learn. But really, to really answer this question of the 5,000 planets, how many are Earth-like? It's driven by telescope diameter. And JWST is just not the right one. We can only really characterize a scant handful, tens of stars. You're going to hear the same names over and over again over the next couple of years. TRAPPIST-1, TRAPPIST-1, TRAPPIST-1. There's like 5 different programs, I think, to look at TRAPPIST-1. But if we really want to answer this question, we need a bigger telescope. We need something that's, able to characterize hundreds of stars. And that's not JWST. And so what is it? Well, our team is working hard to look at the next great observatory, the Astrophysics Decadal Observatory. The Astrophysics Decadal Survey talked about an advanced new telescope. I wrote a white paper saying, I want the Carl Sagan Observatory. That was my contribution. We just heard a few days ago, NASA has chosen a temporary working name of the Habitable Worlds Observatory. And that's what we're trying to do. And we're trying to do it on a human timescale because we can. We believe the technology is there. It's easier than JWST. It's not infrared. We think this will be able to find and characterize habitable worlds and perhaps even tell us if there's some kind of life on it. And so we want to do it soon. That's like 12 years from now, people. That's really super ambitious. But we picked that date because that's the 100th anniversary of Carl Sagan's birth. That was our driver. And it is, I don't want to say it's crazy. I will say it is ambitious. And it's achievable, we believe. We believe it's achievable. And you can ask me during Q&A why I think that, but I do think that. And so that's what we're working towards here. So I'm going to end with 2 messages. One message is for the later career folks. That's us. Is anybody with gray hair? Okay, there's a bunch of you out there. My hair is gray too. I don't color it, right? This is not about us, people. This telescope and then the future telescopes, it's not about you or me. It's about these guys. It's about the young people that I met. It's about all the students I talked with at lunch. It's for the kids, There's a kid up there, it's fire, right? It's not about us. So don't think of it as your telescope. And don't worry if it takes a long time. So here's my message for the young people, all right? For you young early career folks, kids out there, right? Go for it. Get engaged right now, even if you think you don't know anything. And this is why I say that. I got involved in JWST back when I was a young whippersnapper This was my proposal, and I wrote it in 2002, not knowing how long it was going to be. And there's the youngest of my three children, my little baby Lucas, right? And you can see I was young, I had energy. It's like my hair was crazy. I didn't know anything about telescopes. I need to tell you that. But it's worth it. It's worth the wait, even if it takes longer than 12 years. This is the same baby taken the day we got the Neptune images. All right. So it may take a long time, but it's totally worth it. Go for it. I didn't know how long JWST would take, but it's absolutely worth every moment that I've spent on it. So I'm going to end with this quote by Carl Sagan. For all our failings, despite our limitations and fallibilities, we humans are capable of greatness. And JWST is an example of great. We've done a great thing here. And I'm inviting all of you to be involved in the next great thing that's going to come thereafter. So thanks very much.
Well, thanks, Heidi, for a great talk.
Yeah.
Neptune, where's the ring arcs?
Oh, yeah. So it's hard to see them in the composite image. In this blog that we've submitted and is being reviewed right now, we take apart the 4 individual images and you can see the ring arcs, and they're actually not in the predicted locations. And we had a hint of that because even with Keck, we could get a hint of the ring arc of Courage and Liberté, and they were moving. So it's interesting. They are changing their locations. And so we don't quite know why yet. So it'll be interesting to pull that apart once we get the better data set. So they're there.
Great. Questions from the room?
Hey, Heidi, great talk. I was wondering, what's the planned exposure for the longest deep field? That you said it's 12.5 hours.
Yeah, the question is, what's the planned exposure for the deepest field? Vishnu, I don't know the answer to that. I will share with you that for the Hubble deep fields, we were going for days, many days, tens of days. And so I imagine it'll be of comparable magnitude. I just don't remember the actual number.
And anybody online, feel free to put questions in the chat, Bill.
You mentioned chariclo and occultations. What's the plan there?
Oh, the plan is to observe the occultation.
What occultation?
There was an occultation. There was an occultation, and we observed it. And stay tuned. We're working on that. So we wanted to get it out as soon as we could because occultations are possible with JWST. That's what our chariclo observation proved. And so for those of you who like occultations, even of small distant objects like chariclo, they're possible and we can do them and we know how to do it. So stay tuned, Bill. It's coming. It was successful in part.
Other questions for Heidi?
One? Yes, sir. Asking for a friend. So I think you call it day glow on Jupiter speech. How long does that last? Would it light up the night side at any?
Yeah, the question is about H3 plus the day glow on Jupiter and how long it would last. I don't know. We don't know that. I mean, I was surprised to see that. And so
Like hours or minutes?
the fact that it is covering the whole limb of Jupiter suggests that it is much longer than hours and minutes. It's probably days, weeks.
So you would expect some flux from it even on the night side.
Perhaps, but you noticed how it was very thin line. So that's telling you that it's a very optically thin layer, and it was really only able to be detected where it was right at the edge with very high optical depth. So it's not clear you would see it in any other place on the planet. I don't know. I mean, this is one of those questions where we are now having more questions than we have answers. So there's a lot of work to be done on that.
So Jovius Rovers and Sky Frames, maybe to glow. Any other questions?
There was a question, right?
Oh, right.
Yeah, so I really loved your comment about the habitable world observatory. 12 meter, and I was frankly disappointed by the Astro 2020 decadal survey, the 6 meter type. So how do these things relate? What is the feasibility of this 12 meter?
Yeah, so the question is about the Habitable Worlds Observatory, and really how are we going to decide the diameter of the telescope? And that's really going to depend on what our current understanding of Eta sub Earth is and how many Earth-like planets there are likely to be in the sample that we're looking at. So that picture that I showed you of all the different worlds, that is actually the product of a model created by Chris Stark at Goddard Space Flight Center, where he takes into account everything that we know about current exoplanets and their locations and their host stars, and then it spits out a prediction of what we'll be able to detect. And it depends on Eta sub Earth, you know, how many are going to be the Earth-like ones. So, you know, the Astro 2020, they had a conservative choice with their 6.5 meter, but that was based on the assumptions at the time it was written several years ago. What the teams are doing now is they are sort of pushing on various fronts. The science front. What is Eta sub Earth to our best of our knowledge today, right now? And what are the statistics of the bodies? That's science knowledge we need. They're also working on the technological front. How big a telescope can we, you know, effectively make on the time scale that we're trying to make it? So I don't know where yet I would place a bet on what the ultimate size of that telescope would be. We're looking anywhere from 6 to 9 meters diameter. I personally was pushing for 12, but it's going to depend on all those other factors: technology, science, budget, and political realities. All of those things are going to come into play on how we decide where we land. So it's an evolving situation. And what I would say is, if it's something that interests you, to make sure we have this telescope, whenever you hear of opportunities to be involved in astrophysics SIGs or SAGs or teams, or get involved, because we need the voices of our community to support it. It's the only way we're going to get it on a really good, fast time scale. I hope that answered your
And
question.
we're lucky that Ilaria is chair of ExoPay.
Yay. So you know what I mean when I say SIGs and SAGs, right? We're working hard to develop some cross-ag SIGs. This is like, how do you even say these words? This is true. Cross-ag SIGs between ExoPag, CoPag, PhysPag to develop, you know, these science interest groups. That's what a SIG is, to really push forward on the science that we need to know. So I'm sure you and I will be talking in the future as this all moves forward.
So any last question? If not, let's thank Heidi again. Heidi, for the LPLers, is going to be taking off her friendly Loquia speaker hat on Thursday and Friday, and putting on her visiting hat. And we'll be meeting with many of you to understand what the current LPL issues are. So please be sure to come to those meetings and talk to the committee on Thursdays and Thursdays.
I'll still be friendly, I promise.